Okay, good morning. Welcome to this new interesting webinar organized by LSEC ID Lab and the Beacon under the titles of OpenCloudification. It's already our fifth by now, so we're making, I would say, good progress in developing interesting contents, which are being picked up also by you as a audience and attendees in this case. My name is Ulrich Saldenstachts. I'm dialing in here from Belgium, Leuven. And the objective for OpenCloudification really from this partnership is to help companies in Flanders in the first place to get a better understanding of what cloud technologies can offer for them when they are developing their own services and technologies or products, and basically to potentially investigate whether there would be an alternative next to the public cloud operators. But obviously, even considering the public cloud infrastructure, there's quite a number of technologies that can be used to help you basically developing and also maintaining your own technologies slightly better. To start, maybe a short introduction from the side of LSEC here. We are a non-for-profit association, and we've been around for more than 20 years by now. What we try to do is work together with different end users and technology providers, as well as research organizations, in trying to get to the next level of developments in specifically in cybersecurity. But we also take quite a number of new and innovative technologies and bring them into the market specifically for cybersecurity companies to be considered. So we organize different events, both face-to-face as well as online, the one that you're participating in now. And we also support companies as end-user companies directly in utilizing a number of these technologies moving forward. We have quite an extensive membership base. We have today more than 850 direct members, and we do have reach out to about 6,000-7,000 different companies providing technologies in cybersecurity, but obviously also in many different other areas next to cybersecurity, like for instance related to cloud. And so we bring a number of these technologies both to cybersecurity companies, but also to, for instance, manufacturing companies all around. So a bit of activities that we do. In terms of OpenCloudification, it is basically a project that runs for 3 years, but the project is supported in this case by the Flemish government, specifically to support companies in the development of technologies or in the usage of technologies to at least consider what we then defined as open cloud technologies. So it's basically going towards cloud native technologies which have been developed and being provided in open source through end users or technology providers that operate in the cloud or that could operate in the cloud. And then, of course, also a number of related types of technologies such as edge computing, which is probably of interest to many companies out there which are developing tools and technologies, for instance, in the machine making industry. Today, we'll also be talking a little bit about another activity that we are executing in the domain of cybersecurity with and for artificial intelligence, where we've basically developed a couple of platforms already in the past which operate in the cloud. And today, the exercise really try to do that on the basis of open cloud technologies. And my colleague Luca will be glad to show that to you. We have a couple of other types of technologies that we would like to further present, and some of these, like for instance, things like computing on encrypted data, allows us to develop some new types of technologies, and this also brings us to topics like the one of today. It's really where we are supporting technology companies in trying to get the best out of these available technologies. And to give you an example, we are using something which is called secure multi-party computation to develop this platform, which is called Cyber Fundamentals. It's an assessment platform that you can find online, and where the whole idea is to really use the cyber fundamentals basic requirements or guidelines, in this case, offered by the Center for Cybersecurity Belgium, and to put them into action. And it allows us and also you to do a first assessment of your company when it comes to these cyber fundamentals. The website is, in this case, cyberfundamental.eu, so without the S. So here you can basically figure out how these different guidelines could actually respond to you. Now, the interesting thing here is that the information will be stored. You can do that completely anonymously. But the after effect is basically that afterwards, you yourself, as well as others, will be able to see also the scores of others that have entered without going into detail about the specific companies that have entered let's say the assessment, or that have continued in doing the assessments. And then another interesting part of this is if you would be scoring lesser than, let's say, average in this case, for instance, we can help you out by identifying some companies that would be able to support you in the further guidance of cybersecurity. And also this is being done completely anonymously. So in this case, the company that will be able to guide you and to support you further will receive your scores anonymously. And then after the anonymization, you can decide whether you would like to work together with that company to take the next steps. Next to this, also the results of today's session in terms of open cloudification, we utilize in two other mechanisms. One is called DigiHub. So this is basically where we are supporting directly with advisory, but also with technologies, test before invest, companies in the field of digitization. Also, the same is true for Digitalis, which is a European project. So on both sides, we will be utilizing these technologies and providing those to, in this case, end-user manufacturing companies that are looking to further migrate and to further optimize their operations into digital. So really supporting digital transformation on the basis of, in this case, open cloud technologies. So with this, please follow up with us and do make sure that you also check some of the other activities that we organize. I will go and hand over the word, in this case, in the first place, to Marlijn. Marlijn, good morning. How are you?
Good morning. I'm very well, thank you.
So Marlijn, both yourself and Luca are very well known into the open cloudification field by now. You've been presenting a couple of times, and thanks for that. Today, the two of you have some interesting topics as well that you will be covering, so thanks for that. You will be kicking it off with a background also on some of the uses of security into this case the platforms like Kubernetes, microservices, and how to improve that level of security. Before we dive then together with Luca into the domain of AI and specific use cases of AI, and then Marlijn, you will be helping us better understanding how the backend of these platforms, in this case Tengulabs, is working. And one thing still needed to add to this is that the Tengulabs platform that Marlijn will be talking about later on and also be showcasing again is also giving you as companies an interesting sandbox environment to test and play with, which in this case is also what Luca will be showing. So Marlijn, Luca, please take it along.
So as Ulrich said, there is an overarching story for all the sessions this morning, and that is that Kubernetes is more than a container orchestrator. We will be showing a couple of very interesting things that you can do with Kubernetes. For example, I will start by explaining how you can use Kubernetes to implement encryption at rest in your company. Luca will be showing how to do AI and machine learning on top of Kubernetes. And then I will explain how you can use Kubernetes to deploy other Kubernetes clusters so that you can give your developers self-service Kubernetes clusters. And I will be showing this by explaining how the backend of Tengulabs works. So as Ulrich said, my name is Marlijn Sebrechts. I am a senior researcher at IMEC and I teach at Ghent University. And my field of research is service orchestration in the cloud and edge. So basically trying to make the work of system administrators a lot easier. And so I want to start with explaining why Kubernetes is more than a container orchestrator. Because if you go and look at the Kubernetes website and you read their official summary, then it says that Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. So in my opinion, there's two issues. The first issue in this description is that automating should really be bold, because the real value proposition of Kubernetes is to automate operations, but not only operations of containerized applications, but operations of many different things. For example, operations of encrypted storage, of encrypted communication, and other things. And so the best features of Kubernetes is that it provides a standardized API for developers and system administrators to interact with the operations code that manages your applications and your infrastructure. And it provides a standardized API for this code to interact with each other. I will be explaining a little bit more about that second bullet later in this presentation. And so when we talk about automating operations, this basically means that you can use Kubernetes to reuse already codified operational knowledge of things like, how do we do encryption at rest? What encryption algorithms do we use? How do we configure this? And how do we connect it to our applications? Second thing you can do is, how do we do security policies inside of our infrastructure? How can we make sure that each system administrator and each developer only has limited access to the overall infrastructure, so that even when a single developer is compromised, it still only has a limited effect on your infrastructure? Operational knowledge around doing this is already encapsulated in the Open Policy Agent, which is an operator for Kubernetes that basically manages security policies. Same with zero trust communication between microservices. How do we make sure that if a single microservice is compromised, that this compromise can't spread to other microservices? How do we make sure that each microservice is very much contained and has to authenticate with other microservices? And another example of operational knowledge is how to actually deploy Kubernetes itself. This operational knowledge itself is also already encapsulated and available in ready-to-use operators in order to make sure that you can actually deploy and manage Kubernetes clusters using Kubernetes. And so Tengulabs is a self-service portal, a testbed where developers and system administrators can deploy their own Kubernetes clusters on our infrastructure of IDLab. And in the backend, it actually uses Kubernetes to deploy Kubernetes. And so first, I have to give a little bit of background on how Kubernetes itself works. So Kubernetes basically works using desired state models. This means that a system administrator describes what the desired end state is of the infrastructure. This could be things like, I want these services to be deployed, I want this configuration to be applied, and I want these services to be running. And so with a maze, you can compare it with, you get a maze and you say, this is where I want to end up. And then the Kubernetes, the controller, part of the Kubernetes control plane, will look at this desired state, look at what is already the current state, and then create a plan for moving from the desired state to, moving from the current state to the desired state. As an example, for example, if you want a horizontally scaled application running inside of Kubernetes, then you would describe this using a deployment object. So this basically describes the desired state of a single horizontally scaled application. You first say this object, this is a deployment, which means a horizontally scaled application. And then you say each instance of this application has to be a certain container and a certain version of this container image. And at all times, at least 3 individual versions of this horizontally scaled application have to be run. And then what will happen is that a deployment controller reads this desired state and then deploys the necessary containers with the necessary configuration in order to have this horizontally scaled application. And so the deployment controller itself, this is part of Kubernetes, part of the main API. So every certified Kubernetes distribution will have this deployment controller and will allow you to deploy horizontally scaled container applications. However, there is a very large ecosystem out there of third-party controllers which extend the Kubernetes API with additional functionality. So that not only can you deploy a horizontally scaled application, but you can also deploy a database, for example, or enterprise service bus or other applications. And so this is where we come at the first big presentation of this morning. Is I will show you how to use a third-party operator in order to get zero trust encryption at rest on Kubernetes. And Rook is this third-party operator, which is developed in part by Red Hat and IBM. And Vault will be the key management service that we use, also an open source key management service developed by HashiCorp. So Ceph itself is basically open source virtualized storage. Ceph is what we will be using for storage and what we will then be using for encrypted storage. It is very scalable, it is very fault tolerant and provides virtualized storage. It provides 2 types of storage: block storage, so that is virtual file systems that you can attach to containers or to virtual machines. And it will provide object storage using the Amazon S3 API. So that's the uploading and downloading single files. And it has a very interesting functionality for encryption at rest. However, the difficulty is that configuring encryption at rest manually in Ceph is very difficult. And then secondly, you will also need to connect these encrypted volumes to your applications. Doing that manually is also a very complex process. At the bottom of this slide, you also see some of the developers of Ceph. I include this to show you that this isn't a toy project. Like, this is a project that is developed by Intel and Cisco and Canonical and Red Hat, a bunch of very interesting companies that and it's being used by some very large enterprises. So Rook is an operator in order to deploy and manage Ceph on top of Kubernetes. So it's a third-party plugin that you install in your Kubernetes control plane. And then as a result for installing it in your control plane, you get a new type of resource, a new type of object that you create. And the type of this object is a Ceph cluster. And so in your desired state, you define, I want a Ceph cluster. This is the version of the Ceph cluster that I want. And then you have a whole bunch of configuration that you can add. For example, where does the Ceph cluster gets its storage from? How do you want to deploy a dashboard? Which additional services do you want to deploy? But in the default configuration, it just deploys a very functional Ceph cluster with very same defaults for you, is what you can see here. So already by looking at this description of all the different services that are running in order to get a Ceph cluster, you already see that this is actually a very complex piece of software in order to get working. but by using the Rook operator, you have a very easy interface to define what you actually want. And then the Rook operator will deploy and manage and update the Ceph cluster for you. So what you get is Ceph on top of Kubernetes. So I want to give a little bit of background on what the different services are of Ceph. You have the OSD nodes, and OSD is basically the storage daemon. OSD is where all the data is stored. And so these daemons are best deployed on the servers where you have all your storage. And then you have the RADOS gateway. The RADOS gateway is what provides the S3 compatible object storage API. And then you have a bunch of different gateways, for example, iSCSI, in order to provide block storage APIs. And so now that we have a Ceph cluster deployed on top of Kubernetes, we actually want to use this Ceph cluster to give our containers storage volumes, to give our containers persistent storage. The way that we do this is by creating a storage class. A storage class is another desired state model that you create of the kind storage class. And you basically say, if a microservice demands storage from the storage class, then you can get the storage from that provisioner. So this is the Rook Ceph provisioner. And then you can also define where to actually find the Ceph cluster. So it is the cluster with cluster ID Rook Ceph. And you can choose things like which file system will be used for these volumes. And then for each single microservice application, a developer or a system administrator creates a persistent volume claim. And this persistent volume claim, this will give that microservice access to a single individual storage volume. In this persistent volume claim, you first define the storage class name. So this is a reference to the storage class that we just created. You define an access mode. It supports a whole bunch of different access modes. For example, read write once. It means that you have a writable volume for a single service. You can also have read many, for example, which is a readable volume that multiple services can connect to. You also can create a system in which a single microservice has write access to a volume and a bunch of other microservices have read access to a volume. So this is a very useful tool for developers to define the operations surrounding their applications in order to accomplish the tasks that they want. Then they also define how much storage they actually want, 10 gigabytes in this instance. The interesting thing here is that this persistent volume claim, this is already something that a developer can do themselves. So the system administrator uses Rook to deploy Ceph, and then it creates a storage class, but then it just gives a couple of developers access to create persistent volume claims. And so this means that the developers themselves have a lot more ownership over their own microservices. They can easily create a new microservice if they want to, because they themselves can create a persistent volume claim. And already in the backend, Kubernetes will do everything in a safe and secure manner in order to give those developers access to their personal individual storage volumes. So a little bit of a recap. We first started with creating a Ceph cluster by creating a desired state model for the Ceph cluster. Then we created a storage class in order to define in Kubernetes, to tell Kubernetes that it can use the Ceph cluster for storage for microservices. And then for each individual microservice, we create a separate persistent volume claim. Now, how do we actually encrypt this? There are three ways in order to do encryption at rest with Rook. The first method is cluster level encryption. You basically encrypt the entire storage cluster with a single key and with a single encryption algorithm. This already has the advantage that if you have to comply to certain regulations that your data has to be encrypted at rest, then this is already a very good first step in order to enable encryption at rest in a very transparent manner. Like other services will not realize that something has actually changed. So this is a very low cost operation in order to encrypt at this level. However, this has the disadvantage that the entire storage cluster uses the same encryption algorithm, and the entire storage cluster uses the same key. And so if we talk about crypto agility, for example, if you encrypt the entire cluster, crypto agility will be very difficult because you have to re-encrypt the entire cluster in order to switch to a new encryption algorithm. However, the second method is to do service level encryption. This is basically encryption at the level of these persistent volumes. This means that each microservice can use their own encryption key in order to encrypt their storage. And each microservice can, depending on which storage class they use, can use a different encryption algorithm. And so the advantage then is that a system administrator is still in power of what encryption algorithms are used by creating the storage classes. But if they want to switch to another encryption algorithm, they can simply create a new storage class and give developers access to the new storage class, and all new microservices will use the new storage class. And then you can gradually upgrade the existing persistent volumes of the existing microservices also to the new encryption algorithm. So in terms of crypto agility, the second option is much better. The third option is even more granular. You can encrypt at the object level. This obviously only works for the object storage API, but this means that every single file you upload to the Ceph cluster can use a different encryption algorithm and a different encryption key. This is a very interesting solution for complete separation of multiple tenants, for example, or complete separation of multiple teams. Even if they use the same object storage provider, they can all encrypt, they can all use individual keys to encrypt their objects. So now I will give a little bit of explanation, a little bit more in-depth explanation of each encryption method and how you can actually configure it in Kubernetes with Rook. So if we talk about encryption at rest for block storage, the first is cluster level encryption, so encryption of OSD. In order to do that, we basically go back to the desired state of the Ceph cluster that we created, and we add a little bit of configuration, simply saying encrypted device equals true. This in the backend will make sure that it is encrypted. We can also connect this cluster to Vault so that the encryption keys are not stored next to the encrypted data, but are stored in a completely separate service, maybe even in hardware security modules run by HashiCorp Vault. So Vault itself is an open source key management system, basically secure secret storage. It supports very interesting functionalities such as dynamic secrets. It can also encrypt your data. So basically encryption as a service, you send your data to Vault. Vault will encrypt this data with a key that stays within Vault and then send the encrypted data back to you, so that even the microservice that does that is handling the encrypted data doesn't actually have the encryption keys at any point in time. It also supports leasing of keys and renewal of keys and revocation. And one of the big advantages of HashiCorp Vault is that it also supports hardware security modules, both in the cloud and on-premise, in order to have even more security for your encryption keys. So the second way to encrypt to do encryption at rest on Ceph with Rook is to do it at a persistent volume level. So this means that each microservice that requests a persistent volume will receive an encrypted by default persistent volume with a separate key and, depending on the storage class, a certain encryption algorithm. The way that you configure this is in the storage class itself. In the storage class, you explain, for example, which key management system you will use, for example, Vault, and you describe a whole bunch of metadata, for example, so around which encryption algorithms to use. Then finally, you have encryption at rest for object storage. So this works in a very specific way. So you have the client. The client is the agent that wants to store the data encrypted in Ceph. So the client can be either, for example, a JavaScript application running on actual users' devices, or it can also be another microservice that wants to store encrypted data on Ceph. So the client first contacts Vault in order to create a secret key for a certain key ID. This key ID is also a secret itself. Vault doesn't return the key, only says, I have now created a key for this key ID. And then the client uploads the object to the Ceph object gateway. This is the Rados gateway that I talked about before. It uploads the object to the Rados gateway and supplies a certain key ID. Rados then contacts Vault in order to get the key for that key ID. Vault returns the key. The Rados gateway only stores the key in RAM, encrypts the object, and after the object is encrypted, it removes the key immediately, and it stores the encrypted object on the actual storage cluster Ceph OSD. The way to configure this using Rook is, I have to admit, it might be a bit cheating, because Rook by default, it doesn't support object storage, encryption at rest for object storage very well. However, because of how flexible Rook is, you can actually use Rook. You can actually tell Rook to configure specific parameters of the underlying Ceph cluster. And you do this by using a config override, basically where you define within Ceph, you have to add these additional configuration values. So for this type of encryption, even though Rook itself doesn't have a very easy and user-friendly way in order to configure this, you can still use it by basically telling Rook to configure the Ceph cluster specifically for this. And so I wanted to include this specifically to show that even if Rook doesn't support all the Ceph features that you want to use, you can still use Rook, but then specify specific configuration, because Rook has a way in order to then send this configuration to Ceph itself. A very interesting part of this type of storage is that even if the Ceph object gateway is compromised, it still doesn't immediately have access to all the decrypted data. Because, for example, the user uploads the key ID and the Ceph object gateway needs the key ID in order to contact Vault in order to get the right encryption key. As long as the user doesn't send their key ID to the Ceph object gateway, a vulnerability or a compromise of the Ceph object gateway will not be able to actually decrypt the data. And so even though this doesn't completely remove the possibility for a compromise on the Ceph object gateway to decrypt some of the data, it will be a lot slower, and the breadth of the compromise will be a lot smaller, because as long as because the compromise have to be active while the client actually either requests data or uploads data in order for the compromise to be able to see the decrypted data. So in summary, I wanted to start with explaining that Kubernetes offers an API for developers to interact with operations code and for operations code to interact with operations code. Operators add functionality to this API. And Rook specifically is an operator that manages Ceph clusters on top of Kubernetes. You can make this Rook storage available to microservices running inside of Kubernetes, and you can use it to configure encryption at rest with individual keys on a per cluster level, per microservice level, and per object level. So this was the end of my presentation. If there are any questions, feel free to use the Q&A feature in order to ask any questions. And otherwise, I will give the word back to Luca.
Yeah, it's in the first place giving the word to Luca, because Luca hasn't said that much yet. Thank you very much, Milan. We'll pick up some questions potentially coming in later. I see there's a couple of things being raised. For instance, Philip is asking here, how would you go about backup with Rook and Ceph? Is that something that you would like to address now or maybe later on?
I will address it now. It's very easy. It depends on what kind of backup you want. Either you can use this Rook cluster for backup itself, or you can create multiple Rook clusters on multiple Kubernetes clusters, and then basically link the first Rook cluster to the second Rook cluster in order to use the second Rook cluster as backup for the first Rook cluster. Okay, thank you very much. I think that was very concise and direct. Luca, you've been playing around with the Tengulabs platform.
Yes.
How did that go?
Very well, very nice, I would say. Tengulabs is offering a Kubernetes cluster that you can play with, and it's quite easy to start and use it. So
it would be good if you could guide us through a bit on what you've been working at. So as I mentioned in the introduction, you've been also working quite extensively on use of AI in clouds. First using that in the different commercial cloud operators, and now with the opportunity, of course, of the Tengulabs platform, but also, of course, with the experience in cloud systems, a good exercise to see how this can actually work and be deployed. So please guide us through what you've been doing and experiencing, and looking forward to that as well. And Milan will see you back a little bit later on.
Yeah. So good morning, everyone. As Ulrich said, today I'm going to show some little examples on how you can run some AI or machine learning algorithms on Kubernetes. And maybe it's important to say that I'm not a machine learning expert. So the code that we will see today is more to show how to do it than the perfect way to have the perfect model. I hope that if there are experts in the audience, they won't get mad at me for what I'm doing with the data. But the focus again is on showing that we can actually use Kubernetes to run our machine learning models and how to do that. So to start with, the first topic that I would mention is include AI in cybersecurity, because there are multiple features that AI is probably better than us when we're talking about cybersecurity in this case. Some features, well, they might be way more accurate than a human being. But the main thing is that they are able to handle a large amount of data, way more than we could do manually, for example. And they can also adapt over the time and keep learning while they're getting the data, which means that the system can keep improving as long as it receives new data. It's able better than us to recognize patterns or identify threats that might be even unknown. And of course, it's faster to detect and react to any kind of threat that can appear. The use of artificial intelligence, it's also perfectly adapt when we need to automate repetitive tasks. And since it's able to do this fast and deep analysis, it's once again better than us. And the very last point is that you're not the only one that might use AI. AI can be used to create or to support malicious entities that would like to access your data, for example. And probably if you're fighting against AI, you might need AI as well. AI and cloud are a perfect combination because, as you probably know, the artificial intelligence requires a lot of resources and it requires to handle a lot of data. And then a cloud environment is the perfect environment that can provide both and even more. And as you probably know, all the major cloud providers have their own AI/machine learning services that they offer, either via their own platform or their own frameworks to deploy and build and then use your machine learning models as the SageMaker, the Azure Machine Learning Studio, or the Vertex AI. But they also have multiple services that are already AI powered, so improved via AI. And now one of the last hot topic, let's say, as you probably know, ChatGPT is also available in Azure as a service. So what I would like to show today are some simple use cases in which we will use AI to improve our cybersecurity systems. And we will run these simple use cases on Kubernetes. The three examples would be three simple examples in which we will deploy a little network anomaly detector and trying to detect anomalies coming from your login systems, for example. But I will explain a bit more later during the presentation. We will show an integration of what is called the natural language processing, which is basically that branch that relates to the human language interaction with robots or machine learning in this case. I think the easiest way to explain that is what ChatGPT does. And then the last example would be a malware detector that is able to distinguish between a malware and not. How do we do that? Well, in the cloud, there are thousands of ways to deploy your own application with your machine learning models, for example. In this case, we will focus on Kubernetes for multiple reasons. First of all, Kubernetes is a service or a platform that you can basically run in all the cloud providers, and it's also open source. And another reason is that we will use Tengulabs, which is Kubernetes, to do that. So as I was saying, there are multiple ways of deploy your machine learning models. Today, I'm trying to show an example that uses as much as possible open source tools and libraries. So we're going to deploy our Kubernetes cluster via Tengulabs. That would be our cluster, our environment. Then to manage that environment, I'm going to use OpenVPN to create the secure connection with the cluster so I can securely connect to it. But of course, I will also have to manage the cluster. And for that, I will use the standard tool that is kubectl. And at the same time, I will also use another package manager, which is Helm, to deploy the application that are going to run inside Kubernetes. And the application in the specific is Jupyter Hub. I won't explain more about Helm because I have a separate slide for that, and I will talk about it soon. Jupyter Hub is a notebook, some sort of web application that you can access through your browser. And it's an engine, basically a development environment in which you can write your code and test it and run it. It comes with a Python engine, which is usually the programming language that you use for machine learning. And then on top of that, we're going to use the libraries available on Python to then create our models, machine learning models, train them, and then use them. So some examples like TensorFlow, scikit-learn, NumPy, and Pandas, and so on. Those are the main libraries that you would use when you want to create your machine learning model. So the first step is, of course, create your cluster. You need to deploy your cluster. And in this case, as I said, we're going to go with a customized Kubernetes cluster from Tengulabs. I think I'll show the how to do that quite quickly in a second. After the deployment, we will need to download the VPN configuration so I can securely access my cluster and the kubectl configuration file. In this way, even if I'm outside the cluster, like with my laptop, I can still manage it from the outside. And the next steps are to, well, turn on the VPN and connect to the cluster and use the configuration file to manage. So if I can switch my screen, you should be able to see now my browser. I'm already at the website of tengulabs.ilab.imec.be. As we mentioned briefly, this is a sandbox environment that all the companies or the attendees are free to access. You will have to request for the sign up to get an account, and then you will good to go, basically. So in this case, I will log in with my accounts, and as you can see here, I can easily create a new cluster. And at this point, after giving the name, selecting the project and the Kubernetes version, I can customize my deployment, putting how many control plane machine I want, how many worker machines I want, the memory for each worker machine, and the cores for each machine. And then when I click to continue, it will set up the cluster, and then at the end, the deployment would be ready to be used and accessed. And of course, I already have my testing environment ready, so I already downloaded and used my kubectl configuration file, and I can check that everything is working. For example, check nodes, and I can see that I have my master that manages the control plane and one worker, which is the worker that will run our Kubernetes, our Jupyter Lab. Okay. Okay, this is the homepage and the website if you would like to also have your free Kubernetes cluster to run some tests. As I said, I'm going to use Helm as a package manager for that. And the reason is, well, it simplifies the deployment of applications and the managing of that. As Merlin also showed, when you need to deploy something on Kubernetes, you will have to write some configurations files like the deployment and the services and the volume claim and so on, that are YAML files that you have to write and prepare and configure, and then ask to Kubernetes to create or to deploy an application based on the configurations file that you created. Well, Helm tries to do that in an automated way, and it does that via what they call the packaging format that are charts. And it's basically the collection of these files that describe what you would like as a configuration and as dependencies. And of course, together with the charts, you will still have the possibility to modify some values in another file and then customize your deployment. But since the shards are stored in repositories and can be accessed by Helm itself, but even by the community or the owners of the various tools, it's very likely that for the application that you would like to deploy, someone or the company itself would have created the charts that are the best way to deploy that type of application. So that's what I'm doing on deploying Jupyter Hub. I'm connecting the repository that comes from GitHub, from the Jupyter Hub GitHub. And after updating it, I'm just running one line of code, one line command that asks to install what I will call Job Hub, which is basically Jupyter Hub, the repository, Jupyter Hub chart. And then I can still modify some values to customize my deployment. And then Helm will basically interact with Kubernetes and deploy Jupyter Hub in my environment. Then, of course, I will have to check whether where my application is available online. Like in the Tengulabs environment, I'm still in the local address. So I'm not having a public address that can be available by anyone. So I'm still using my VPN to connect the Jupyter Hub. But at this point, once I deployed it, basically I already have the access to my Jupyter Hub notebook, and I can start writing my code, in this case for machine learning. Before showing some actual code, so some live demos, I would like to add some information about the first use case in this case, but I would like to add two points on that. First, what's an anomaly detector? If someone might wonder what we're talking about. Well, a network anomaly detector is a system or a tool that usually runs within your network. And based on the logging or the access that users, other application, etc., all the traffic that goes through your network tries to identify whether there is an anomaly or not, like something that you wouldn't expect from a standard user connecting, for example, or some behavior that usually is a bit odd. So it tries to guess that and classify it as an anomaly. And at that point, maybe send either close the connection with that application or user, or send an alarm to an administrator, for example, that something is not behaving correctly. And related to the Python code, as I said at the very beginning, I'm not an expert either on Python or machine learning. So I'm trying to picture here as in a nutshell, what you would do if you're writing your Python code and you want to create your machine learning model. The first step is always to import the libraries in Python that you would use for your modeling. And then a big part is the preparation of your data set or your data that you would use to train your model. This is usually the biggest part because it requires a lot of time of effort to perfectly customize and adapt the data to better pass it through the model. And it works with the logic of garbage in, garbage out. So basically, if you're not passing nice data, probably you won't have a nice machine learning model. Well, in this case, I'm not doing that much of preparation. That's why our models won't be the best in any case. But again, this is a showcase. Third step, you define your model and you train it with the data that you prepared from your data set. And in the fourth step, you will evaluate the accuracy, the precision of your model to see whether it's capable or not to perform the task that you would like to be achieved. And as a last step, you can now free to use your machine learning model with new data. Okay, so we start with the first examples. The first example, I'm already on the Jupyter Lab notebook that I created, and I'll show the code for the anomaly detection. As I mentioned, the first step is to import all the libraries that I will need to deploy my anomaly detection. Pandas, scikit-learn, NumPy, matplotlib, and so on. Those are all libraries that are used in machine learning for arithmetics, the machine learning models, visualization, and so on. Then there's the second step, the dataset preparation, which is, again, the big part, and I'm just going through the very basics on that. The dataset, the data that we are using to show that is a public available dataset. It's called KDD Cup. Basically collects 75,000 or even more lines or entries of network logins with all the metadata on that, and it labels whether that specific entry is an anomaly or not. So what we're doing during the preparation is what we want to achieve is we don't focus in this case on the specific anomaly. We want just to have whether there is an anomaly or not. So we're returning 0 or 1. We're changing the dataset for that. And then we're choosing the model that we will use. In this case, is isolation forest. It's one of the machine learning models that is usually used when you're dealing with anomalies. And how it works is basically create random pattern, and then based on this pattern, try to isolate the anomalies. Like for each category, if there's a value that is out of a range of values, then it's probably put aside. And if you could iterate that with the iteration of that, you will start separate the anomalies from the rest of the normal entries. As a normal step, you divide your dataset in two. And the first one would be the train set, so the one that you will use to train your model. So it has the values that you're entering and the label that says this entry is an anomaly, this entry is not. And then what you would do is test your machine learning algorithm with the second part of the dataset, the smaller section, in which you pass only the data, and then you confront the result that the model gives you with the actual label that says this is an anomaly or not. So we use isolation forest for that. As I said, we started and train it. This is the Python code that trains it. And of course, we can print all the scores or the values. There are hundreds of different representations that you can see to help you modifying or adapt your data. Now I'm going quite fast on that. And as a last step, we basically check whether it's able to predict or not if an anomaly occurs. And in this case, then we're computing all the various values that are available and used in machine learning to see how precise and other factors that are used to evaluate the quality of your machine learning model. And in this case, we can see, for example, that the precision of our model is a 62% precision, which is not that much. But again, it's a model that the data wasn't being adapted to the model at all. So 62% with just a basic algorithm is quite a good result, I would say. But of course, in this case, what I'm doing is uploading the data set together in my testing environment. But that's not something that you would usually do. What you would do probably is that you're storing your data somewhere else. And that could be, for example, on a S3 bucket. So if your application is running in, let's say, AWS, you probably have your system that runs. You have your system that runs within the AWS cloud, and probably through an API gateway or directly to the S3 bucket, you're storing your data and new entry in this bucket. And then what you might expect is, for example, that you run some Lambda function on that, for example, for each new entry in the S3 bucket, you can automatically trigger the request to your anomaly detection system or your anomaly detection model and see whether that's a legit access or an anomaly. And in that case, maybe you can have a system that also send a message, for example, to the user or to an administrator and so on. So you can do that, of course. There are Python libraries that let you interact directly with the S3 bucket or with any other Amazon service, as an example. But at the same time, let's say you want to stay within Kubernetes. And as Merlin said, like as for the storage, the encrypted storage, you might have Rook steps. And in that case as well, you can write your own code using the Kubernetes libraries, and then have the data coming as a stream from a data set or a database or somewhere that is stored within Kubernetes, and then use your model for the new entries to check, to train, and then to store data and to predict the anomalies. And another quick example, I won't go too much into details in that as well, is, for example, the use of PyTorch, which is the neural network. I think is, again, one of the most famous libraries, but also frameworks. In this case, PyTorch can be deployed and run in Kubernetes as an ecosystem in which you can then write your code there in a distributed environment. Or it offers some functionalities as a library that you can install and use in your Python code. So I rewrote the same code, and in this case, I'm using a little neural network with just 3 layers that trains on the same data set and then tries to classify whether or not there's an anomaly. In this case, the results are quite better, but of course, not doing data pre-processing means that there are still some settings that need to be adapted. Okay. Second example would be a quick one. I also see that I'm running a bit late. The natural language processing, as I said, is the part that handles the human language. In this case, would be English. And I will show a quick integration with ChatGPT because, yeah, it's a hot topic again. And in this case, you can imagine that what you would have is, imagine that you have like a ticketing system or a support system that you can use for your customers or for your employees. Like instead of editing something that needs to be handled by humans, you can have the first interaction with a bot. That's something that we starting to see quite often everywhere. So the example that I'm showing here imports the OpenAI library, which is the one is the company behind ChatGPT. And I created a little script that basically sent a message to one of the last releases of ChatGPT, the GPT 3.5. And in this case, since ChatGPT is always quite busy, I just sent the request in a moment that it was available to reply to me. And for example, I'm sending here a message saying, provide me a list of tasks to perform as a pen tester. So the reply that I get is something that says that it's a list of 10 steps that a pen tester might consider while he's doing his job. Of course, we know still the limitations of ChatGPT. I'm not dealing into that right now. But that could be seen as a support service, like, oh, I know that I need to perform some steps, and maybe ChatGPT could help me remind me what are the steps that have been done. Of course, they might be adapted to your use case. This other little script instead uses the previous version of ChatGPT, the Text DaVinci, which is quite less busy usually. And in this case, I'm showcasing here that you can have an interaction with it, saying, for example, I would like to have to store securely my keys in the cloud, and then you have all the interaction like, would you like to know more about the services? That's something that you can put, for example, where you would like the customers that are starting asking some generic questions to be addressed on the different stages, like the cloud storage solution, but you can interact with it. This is, in this case, a live interaction. And of course, what you could do instead of having a prompt here is the integration. And instead of me sending the message right now, it could be directly forwarded from your customer. So you get the reply and then you send it back to the customer. Last example, malware detection. In this case, I don't know if I have to explain what a malware detector is. I think it's quite self-explanatory. We try to write a code in Python that it's able to define whether a specific application is a malware or not. To do that, we're following the same procedure. And in this case, I'm using another publicly available dataset that is called dataset malwares. It contains portable execution files, so PE files that I think are from Windows. These are the list of all the features or all the components that are for each entry of the dataset. And in this case, I'm using another classifier. Again, we're classifying. We want to know whether a specific file is a malware or not. And I'm using the random forest classifier, which is similar to isolation forest with some differences. I'm not going into that. But the procedure is basically the same: divide in training and test set, train our model first, and then pass the data and evaluate the accuracy of our algorithm. And in this case, even without that much of pre-processing, we can see that the model itself is quite good on identifying whether the file that I'm asking is a benign or a malware, is a benign file or a malware. Even from the heat map, you can see that it predicts correctly, like most of the cases. So at this point, what would be useful as the last step when I mentioned the 5 steps on using machine learning would be that, okay, I trained my model. I know that it works, but this is still a testing environment. I would like to start using my service or my model. So what I can do is save this model. And one of the standard ways of doing that is to create a pickle file, which is a file that contains my machine learning model that I will be able to load it somewhere else, in which the model is already trained. So it's just the machine learning model, and I can pass the data through it and then get the result that I want. And in that case, this could be an example to stay within Kubernetes. So I trained my data through Jupyter Hub. And at this point, I might run it in another container, in another image that I can, for example, create my custom image that contains the malware detection model, and then make it available, in this case, for example, using Flask, which is another open source library that creates a little server that can get requests and reply. And it could be managed from Kubernetes, for example. And then users or other machines or other applications can directly send the request to Flask. So how do you do that? In this case, for a matter of time, I will show it in Docker file, in a Docker container, which is quite faster because I will run it locally. what you do is create your custom image of your container that will contain also the machine learning algorithm. So you can create with the command docker build, and then you give the name of your image. Oh, sorry. And then you can run a container that contains your model. And basically, for example, using Flask as a server, you can directly contact it and interact with it. And that's what I've done. I created the little server that I will put on that. And this is, for example, the Docker file that starts from a Python image that contains the bare minimum to run Python code, and in which I will upload my machine learning P code file and my little server, and I will open it in a port that will run as a localhost. And after doing that, I can use Docker. In this case, would be in my local environment. After creating the image, I can run a container, for example. In this case, it's called example. That contains my machine learning model. So what I can do is create a little script that sends a request to the specific to my server, and I know that in my file there are 10 entries. The first 5 are malwares, and the last 5 are non-malware. What I'm expecting is that the server will evaluate them and then return it values that are 1, whether it's a malware, and 0, whether it's a benign file. So I send the request. It's a little Python script, as I said. It processes it, it receives it, processes it, and gives me back the results. And in this case, as you can see, the first 5 are malwares indeed, and the last 5 are benign software. Now, of course, this is an example, a quite simple example that you wouldn't use in a production environment, for example, because you wouldn't expose your machine learning model directly to the internet, or like access give the access to anyone who is in the network. So what you will probably do is create some sort of gateway or a server in between that gets the request either from users or from machines, and then through the authentication system might provide the access to your machine learning prediction model. Or another way to do that is to have it automatically running, for example, and in this case, your monitoring system or your logging system, your upload system, anything that uploads data to your database, for example, which can still run in Kubernetes, then can trigger a function or a batch script, a serverless function, anything that can be run in Kubernetes again. And this service will then ask for detection or prediction, for example, and in case of a malware, send back an alarm that can be forwarded to user or the machine. Okay, these were the 3 little examples. What are the conclusions of this presentation? Is that, artificial intelligence and cloud can get along pretty well together, because as I said, it requires a lot of resources and data, and the cloud can provide that. But also in the cloud, there are a lot of applications and frameworks that can be used. At the same time, there are hundreds of open cloud tools that can be used and are already available for your machine learning purposes. There are a lot of opportunities. We showed some examples related to cybersecurity, and those are like a little number of examples, but there are dozens, even in this case, just related to cybersecurity, but you can apply artificial intelligence to a lot of different topics. And why I showed in Kubernetes, that's one of the key points of this presentation is the fact that offers a better portability, but also resilience and sovereignty for the cloud and your on-premise environments, because basically you can move your Kubernetes clusters in different environments, and more or less the configuration stays the same. And at the same time, any major cloud provider or any public cloud provider has its own version of Kubernetes. So you don't have to completely rewrite your or re-architect your entire deployment. But of course, it requires the knowledge of using, in this case, Kubernetes, for example, and all the tools. Tools and frameworks, there are, again, a lot. For AI, I mentioned some of them with the libraries or Jupyter Hub, for example, but there are way more tools that can be explored based on your use case and based on your needs or your knowledge. Okay, that was my last slide. For more information, questions, comments, not on the machine learning side, but for anything else, keep following us. And if there are questions, I'm always here and I can answer to them.
Thank you very much, Luca. Yeah, I think that makes a lot of sense in many directions. Definitely on the follow-up, definitely on the websites here, also on the CSAI.network website activities. So I'd suggest basically, I mean, definitely for people in this space, do try out Tengulabs. I think one of the next things that we can do is organize a bit of a workshop on how to set it up, and then in this case, Luca and others in the teams can guide you physically, as in practically, on taking the next steps and basically doing some exercises in how this actually needs to be set up and working. But also, like Luca was indicating, there's so many different tools out there that could help you making those first steps in AI, and this is really the perfect place for this. You can take some sample data from your networks, take some sample data from devices that you can easily collect with some monitoring tools, and then put that into this environment to test out and to really see what you can get, and also to showcase what actually the benefits are in this case of AI for cybersecurity, and at the same time, of course, seeking out how you could deploy it yourself with open cloud technologies. So yeah, thanks for that. Thanks also for taking us to those very many difficult steps. I think it's quite a challenge in learning all of the different individual steps, and so you've done that greatly in the last half an hour. I think it takes us back to Marlijn, and now that we've seen basically how to secure an environment, how we can also do a use case basically in the Tengulabs environment. I think it also does make sense to take a bit of an insight in how Tengulabs really works and operates, and what it really looks like, and definitely also from the back end, how it can actually work. So putting here to see if we can get Marlijn back into action.
Hey Ulrich, you will probably need to start my video again.
Yeah, I was trying to do that here. I've started to ask to share. Yeah, there you go.
Okay, that's great.
Luckily, there's something like privacy, so you still have to accept it.
So
right.
Since we use Tengulabs, we use Kubernetes to deploy Kubernetes and to basically give users a self-service portal for deploying Kubernetes clusters. We thought it would be interesting to also explain how it worked in the backend, not only to show you how you can what an easy way is to deploy supported Kubernetes clusters, but also as like a few tidbits that you can use to create self-service portals in your own company. Since Kubernetes is this massive API that connects to all your operations code, it's very easy to use Kubernetes native tools in order to then give developers, for example, the possibility to request storage, to request SSL certificates, to request VPNs and things like that. So we will explain how we do this for Tengulabs, specifically to allow developers to request Kubernetes clusters. But these same tools, most of the same tools, you can also use to request anything, because they all interact with the Kubernetes API. So first, a little bit of history of Tengulabs. Throughout OpenCloudification.
Sorry, Merlin, that I'm stopping you.
Yep.
I don't know if it's my issue, but I cannot see the.
No, it says here
your
that
screen.
Milan started screen sharing, but it's not yet appearing. I was just going to say about the same thing, Luca. Yeah, now you
okay.
can see her.
All right.
Thank you.
And can you see me change the slides?
Yes, we can.
Great. All right, so a little bit of history. Throughout the OpenCloudification project, the next 3 years, you will probably see the name change from Tengulabs to Cloud Native Lab. And I wanted to give a little bit of history. So we created this test bed because inside of ID Lab, we were doing a lot of research on cloud native tooling, on Kubernetes, on operators, and on applications that are running on top of Kubernetes. And we saw that a lot of these researchers, they lose a lot of time simply by trying to deploy Kubernetes clusters themselves. And so we decided to simply create a test bed where with a few simple clicks, researchers can deploy their own Kubernetes clusters to let them get to the actual research on top of Kubernetes instead of having to mess with installing Kubernetes itself. So the first version of Tengulabs is online right now at tengulabs.ilabday.imac.be and is available for people in OpenCloudification, part of this project, to use. We are currently working on a Tengulabs education instance, which should be done by April of 2023, about around mid-April 2023, which we will use first inside of Ghent University to teach our students how to work with Kubernetes, and then later can be used for other educational other courses. And then in the fall of 2023, we expect to deploy Cloud Native Lab, which is basically the same functionality as Tengulabs, but with a new name. And then it will finally be a full ID Lab testbed. As I said in one of the previous presentations, one of the previous sessions of OpenCloudification, the current hardware that we are running on will be end of life at the end of this year, and so by the fall we will put our entire stack on a new cluster, a very beefy cluster, which will allow us to make Tengulabs generally available to anyone within our research group and anyone associated with our research group to use. And then for 2024, we will be focusing on Cloud Edge functionality. So right now, it simply deploys a Kubernetes cluster, but we also want it to be a place where developers can test Cloud Edge functionality, for example, Kube Edge, a Kubernetes distribution with functionality to also deploy workloads on edge devices. And that's coming in 2024. So a very quick overview of the backend. We use Cluster API to actually deploy and manage the Kubernetes clusters. Cluster API is an API that is part of Kubernetes itself. It is thus a standardized and fully supported API of Kubernetes itself that allows you to deploy and manage new Kubernetes clusters by creating a desired state model where you request a Kubernetes cluster. Specifically, we use the CapV plugin, which is a plugin that then deploys the Kubernetes clusters on VMware vSphere. This plugin is part of the backend of VMware Tanzu, their VMware's commercial Kubernetes cluster offering. So in that way, you know that you are using a supported and a battle-tested plugin in order to deploy Kubernetes clusters. Then we use Argo. Argo is a Kubernetes native project. We use it for workflows, for GitOps, and for CI/CD. Specifically, we use Argo workflows in order to call certain actions, like create a Kubernetes cluster, and then monitor the status of those actions. In Tengulabs itself, you will see that once you create a Kubernetes cluster, you have a status page which shows which step of the creation it is in. This is all done using Argo workflows. And then we use Argo CD in order to actually modify the Kubernetes objects. Like Luca, this also uses Helm in the backend. So we ask Argo CD to actually, hey, please deploy this desired state model for us. And then Argo CD will do everything in order to make sure this works. And then finally, for the connection from your laptop to the cluster, we use Easy OpenVPN server. So in order to explain the features of these different pieces of software a little bit better, I'm just going to go through what actually happens once you click Create Cluster. So the first thing that happens is that the JavaScript in your browser, it contacts the backend Tengulabs API, which is a REST API that is simply using Python Flask. This API is incredibly bare bones. It really doesn't do a lot. It gets a call. It saves the state of what is requested in Postgres. It starts a job to create a cluster, and then it just returns success to the user, and then it stops. And so the API itself doesn't have like a job queue, doesn't have long running processes. It's simply an API that starts a job, starts a workflow, an Argo workflow, and then basically returns. And that means that it's a very lightweight code base, incredibly easy to maintain. Then this job that is started is an Argo workflow. So Argo itself also has a REST API, which you can connect using Argo events to a workflow. So we call a REST API and we tell this REST API, hey, create a Kubernetes cluster using these properties, and that will start the create cluster workflow, which you can see here. So Argo itself, since it is Kubernetes native, you actually define these workflows also using Kubernetes objects. So it's a Kubernetes object of a kind sensor because it reacts to an event to the REST API. And then it has a graph, a direct acyclic graph. So basically a workflow with 3 tasks. First, create cluster, then wait until the cluster is available. And then once the cluster is available, it installs the CNI, the networking interface. And then afterwards, when everything is done, it reports back to the API, to the Tengulabs backend API, in order to say everything is ready. Then what actually happens in the backend, so this workflow, it tells Argo, so the workflow that is shown here, it tells Argo CD, now deploy this application on top of Kubernetes. And then the application itself is basically a new cluster. And so cluster API is the thing that creates a new cluster. And this is how desired state model for a new Kubernetes cluster, what it looks like. So it is of type cluster, and then you give it a whole bunch of configuration, like which IP addresses should it use, which network range should it use, And so this is an object that we persist in the management cluster. That's what you can see here. The management cluster is a Kubernetes cluster that always keeps running and that is connected to VMware vSphere in order to deploy new clusters. And then this management cluster will look at the desired state that you got. So we want a new cluster. Look at, is this cluster already running? No, it's not running. So I will run it. And then it can deploy on a whole bunch of different Kubernetes providers. But what we specifically use is VMware, the VMware service. But it could very well also connect to AWS or Google Compute Engine. Cluster API is very flexible in that regard. So then we have the question. Then we have a question. So you have here the management cluster. This management cluster is what we use to deploy new clusters. But then the question becomes, what deploys the management cluster? The management cluster itself is deployed using a sort of bootstrap method. So what we first do is we create a very simple Kubernetes cluster on our laptop using kind. Kind, it stands for Kubernetes in Docker. It's basically a Kubernetes container that you can install with a single command on your local device, on a laptop, for example. It's a very easy way to get started with Kubernetes on your laptop. And so what we do is we install kind on our laptop, and then we install the cluster API provider for vSphere inside of this Kubernetes cluster that's on our laptop. Then we use this cluster API instance on our laptop to create the first management vSphere cluster. Then we install cluster API also on this management cluster that is running inside of vSphere, inside of VMware virtual machines. And then we can use that to actually create workloads clusters. However, we do one step more. We also migrate the cluster that we are running on top of our laptop. We actually migrate the control plane to the management cluster running inside of vSphere, so that this management cluster in vSphere can actually manage itself. And so by that point, we can just shut down our laptop and remove the cluster from our laptop. And by that point, Tengulabs is completely bootstrapped and now manages itself inside of vSphere. So since these clusters are actually running inside of our own Tengulabs network, they are not by default accessible from the outside. They are shielded from the internet. So that means that you need a way to actually connect to the Tengulabs network in order to be able to access your Kubernetes clusters. We do this using OpenVPN. However, if any of you in the audience have ever installed OpenVPN by hand, you know that this is a very complicated process to do. And either you get a commercial offering which installs OpenVPN for you and manages certificates, or you have a very painful process that you have to do by hand. So for this reason, in order to solve this issue, we actually created Easy OpenVPN Server. This is a single snap, so a single installable package, which installs an OpenVPN server for you on your server, which will automatically detects attached networks and attached routes, and automatically detects what the default gateway is, what the IP address is that users will connect to, and then generates first the configuration for the OpenVPN server itself. And it also generates client configurations. The OpenVPN server itself, it has a number of security best practices such as that it uses a pre-shared key so that the server itself is protected against DDoS attacks, and it does authentication using X509 certificates. And it generates all this for you. You don't have to do anything. You just install the snap, it generates everything for you, and then you have a single command to add a new user, which gives you a single OpenVPN configuration file that the users can use to install it on their laptop or on another device, on another server, in order to connect that device to the Tengulabs network. One of the advantages of this approach is also that this OpenVPN server, it has multiple fallback methods to connect. And the last fallback method, it punches through firewalls. So first, it tries to use one of the most performant protocols in order to connect to our network, which is UDP using the OpenVPN port itself. However, a number of internal firewalls will block this traffic. A number of enterprise firewalls will block this traffic because it's sometimes used by malware in order to gain access to something. So as a fallback, it disguises its own traffic as basically SSL traffic, so HTTPS traffic, in order to punch through almost all firewalls. The only way a firewall could actually protect against this VPN is by doing an analysis of the traffic patterns itself in order to figure out that it's not actually an HTTPS web page, but a VPN. So we do this because we collaborate with a number of other universities, and for some reason, some of the Belgian universities have incredibly limiting firewalls, but we still need to work together with people in those universities. So the VPN server has the fallback to disguise itself as HTTPS traffic. Then we also do authentication and authorization using Fat4Fire Plus. Fat4Fire Plus might not be very known outside of the research community, but it's a Europe-wide federation of research testbeds. The Fat4Fire project itself, it has currently ended. It was a European Union funded research project. Even though the collaboration and the federation still exist, the project itself shut down. And so now we have a new project, which is called Slices SC, which basically continues the legacy of the Fat4Fire project. And so inside of ID Lab, inside of our research group, we have a number of different testbeds, which are all available through the Fat4Fire Federation. City Lab, for example, allows you to deploy applications on top of a whole bunch of IoT nodes, which are located in the city of Antwerp. GPU Lab is a really easy way to run GPU workloads, for example, AI workloads or machine learning neural networks on top of our data center. And then we have the virtual wall, which is a very easy way to create physical hardware and virtual networks to connect this physical hardware. It is often used for research on network algorithms, for example, video distribution algorithms. And then Tengulabs is another one of these research testbeds that we have. And so the way that we integrate to the Tengulabs, that we integrate into the Fat4Fire Federation is using OpenID Connect authentication. So Fat4Fire has this product called the Fat4Fire portal, which is basically an OpenID Connect portal, which you can integrate into your own web application in order to enable authentication and authorization. And the advantage is that this portal, it actually integrates into seamlessaccess.org, which is a service that connects an incredibly large number of university single sign-on mechanisms. So students at Ghent University or students at another university can simply use their university login in order to log in into this portal, and then thus log in into Tengulabs. And so if you want to use Tengulabs, if you go to the URL, you will see a sign up process. If you're not a student and you don't have a university ID, if you're not a student or a researcher, and so you don't have a university ID, you can still request a specific account for Tengulabs. And so the Tengulabs website, it explains how to get to our Slack instance to contact us to receive a personal access account. And so one of the advantages of using this Fat for Fire portal is, well, first of all, that we integrate into all university accounts, a very large number of university accounts. And the second advantage is that things like sharing resources. So if one person creates a Kubernetes cluster and they want to share this Kubernetes cluster with another person, this is actually already, we get this for free simply by using the Fat for Fire testbed portal, because it has this concept called projects. And so everyone who is part of a certain Fat for Fire project has access to all the resources in that project. It also allows us to get the SSH keys of the user from their Fat for Fire profile in order to add them to the Kubernetes nodes, for example. And we also use it for admin permissions. We have this project called Tengu, and everyone who is part of the Tengu project has admin permissions in Tengulabs. So this was a broad overview of how we use these technologies. I think the most interesting technologies are, first of all, the Argo project with Argo workflows in order to have like a certain job mechanism with different steps. Argo CD in order to actually deploy applications on top of Kubernetes in a robust and fault-tolerant manner. And then Cluster API in order to deploy the actual Kubernetes clusters. I guess there is some time for questions now. If you have any questions, you can ask them in the Q&A section of the Zoom interface.
Yeah, or of course, ask us afterwards at another point in time. But in any case, thank you very much, Marlijn. That was very insightful and useful, and I think also inspiring to many different considerations. On the one hand side, trying to see and definitely for other organizations to learn that they can use these technologies to maybe even set up their own architectures for testing purposes and the and deploy their own sandbox environments. On the other hand, there's definitely also this interest that we can now provide. Hello, Cat. We can now provide for people to start testing this out. So, like Luca was showing, an environment that helps in easily deploying your first test cases yourself. And building out basically from scratch in a couple of hours and a full proof of concept on different types of technologies as we've seen. And of course, whatever you develop, it's not completely wasted, because you can just pick it up, whatever you put in there, copy it and then deploy it again into another either operational or other sandbox environments. So start with Tengulabs, deploy it there. If it works, further improve it, and then basically deploy your own architecture either at home or in your garage, or in a public cloud environment. So it really has all the flexibility that that one can imagine. So I guess there's many different use cases that we are going to explore now with all of these different pieces and technologies. And like I suggested also with Luca, I think also for the next occasion, we will be able to set up a workshop where we can detail this even a bit further and actually guide different participants in taking this to a practical console level type of experience instead of just the presentation, of course. So if that's of interest, then do reach out to us. We'll be happy to facilitate that. I think maybe something that's an interesting question for the both of you to consider, but I think you in the first place, Marlijn. We have been seeing a couple of manufacturing companies that have been basically building their architectures on the basis of either legacy environments, client server types of applications, and are considering definitely new types of architectures. How would you see this basically on being deployed even in an edge level, whereby we could potentially set up a sort of a mini container in the environment of an industrial machine, and basically using that as a server environment for the basically the operator to start operating the machine, or maybe so much operating the machine, but at least to do controls, to check some data, and maybe also be further inspired for additional learnings, like using video materials and manuals and so forth. Is that something that that you think is feasible? Maybe it's something for the next webinar on the 18th.
It's a very interesting question, and it's something that we will dive very deep into for our next webinar. And the answer is obviously it depends. If you talk about Kubernetes, for example, if you have the resources in the edge in order to run Kubernetes, it's a very interesting thing. It's very useful to then actually run Kubernetes on the edge, because it gives your developers a very easy way to update applications quickly, even applications in the edge, to test, to develop, to get an overview, to have better monitoring, and you get this entire ecosystem of Kubernetes on the edge. However, the caveat is that Kubernetes itself, it is very resource hungry. It takes often at least a gigabyte of RAM in order to simply run the Kubernetes control plane with minimal services running inside of it. So that means that you really need beefy devices in the edge. If you don't have those devices, then we have some ways we can help you, and we will dive further in it during the next Open Cloud meetup, because we do a lot of research in how to shrink the resource usage of Kubernetes in order to make it fit on edge devices. And we have a couple of ways that we try to tackle that. We have a couple of different projects that we are developing inside of our research group that we will discuss further during the next session. Another way to go about this is to simply use Docker containers themselves, because Docker containers without Kubernetes have a lot less overhead, which can run on edge devices very well. And then a third way that's also very useful is to look into alternative ways to package your applications, which is like looking at Ubuntu Core, which uses snaps. Easy OpenVPN server is also such a snap, which is something comparable to a Docker container, but which is specifically built for edge devices and for integrating with your hardware on edge devices. That's a very interesting project to look into also.
Okay, let's definitely take that up. So maybe it's a good moment, also, of course, as well to elaborate a little bit on the program for the next event. I said our next webinar, but it's basically going to be a hybrid event. That's going to happen on the 18th of April. So in less than a month's time, will take place in Ghent. And so the on the page that you subscribed here to, there's also a link already to that registration address. So please do follow it. The focus, indeed, as Milan was already indicating, is to dive into some of the edge development cases and to really highlight some of the experiences that we've been able to get there. Also mainly serve to inspire. And as well in conjunction, let's say, aim is to already see if we could deploy some and develop some materials for further research and reading through in the form of white papers and other documents that could get you started in that route as well. Any additional thoughts, gentlemen? None whatsoever. Okay. Then with this, I suggest, unless there's any no further questions, I thank you for your both of your works and presentations, and do keep up the good work there. I'm looking forward to seeing some new developments and deployments in the next series of events, and to our attendees, of course. Hopefully, we'll be able to meet now face to face again in the next session. So thank you very much all for attending and for presenting, of course. Have a nice rest of the day, and see you very soon. Thank you.
Bye.